Hi, welcome to Hardware Design. Today we're going to be talking a little bit about counters. This is meant to be a makeup lecture for the course I'm teaching. So counters are this reoccurring structure in a lot of designs. So if you find that you need to sequence something, usually the base sequence element is a counter. The other place this occurs a lot is when you have interesting data structures. You often use these to keep track of the pointers. So I've found that you can save a lot of effort by just maintaining one counter that you're sure works with the parameters to try and keep track of what's going on. So this is kind of based off a discussion that we had maybe I think Monday, where we were talking about unit testing and sort of the value of maintaining one unit with a tight set of tests. And there was some confusion in the discussion between students on what exactly would this look like in practice. So what we're going to do for this makeup lecture is we're going to spend maybe the next 30-40 minutes trying to quickly hammer out exactly what this looks like. So the place to start is with a new file. So we're going to, hopefully we didn't lose anything important. Closing that out. Oh yeah, that's some old vlog stuff. All right. So the first thing we'll do is we will Emacs minus fn mono. I think 14 is pretty reasonable, and we will do RTL slash. Let's see, how many counters do I have? So it looks like we have. We'll call this counter gen.vp, and then we'll make a verif slash top under counter under gen.vp. So this is the kind of general pattern that we have, is that anytime that we build something, we're going to build the top at the same time. So we're going to take a peek at some of the other tops that we have just to steal some syntax. So we'll do top integrator. So this is one of the homeworks coming out. So it looks like we always start with our good messages. It's not a bad idea to have a comment at the top to indicate where this is coming from. So this is top under counter gen. Module, backtick mname, backtick. So that's that guy. We're going to make sure that we end with an end module, and then what we're going to do is we're going to create our dot. And so in the make file we've been using, we always call generate base, and then we're going to call it on counter gen, and then the instance name must always be my under integrator. Perfect. Uh-oh. Seems to not want me to delete that. Good. So that's that. And that's kind of the bare minimum for now, but in a little bit we need to, so let's see. So we have a generic bench that sets up the environment, so we'll add that. And it looks like we have some miscellaneous things here. I think mostly this generic bench is going to set up clock and reset. And then we can instantiate them so that the compiler actually runs with those. Great. And then we need to build the interface for our module. The So that's about enough now to get going. Later on, we'll need to add some stimulus. We'll need to add some narrative stuff, so we can still steal the simulation narrative for the integrator. That's probably good enough. Yep, so we run for a little bit. That works for me. And then, do we need anything else? So it doesn't look like we need anything else right now. So far, what we have is we have an instantiation of our DUT and our generic test bench, and we have something to sort of provide the simulation narrative. So how long we're running. So we can switch over to our counter. And we should probably start the same way. Module mname. Though in this case, we're going to have some inputs so that this gets formatted in a way that's kind of reasonable. So we'll start with the most basic counter that we can. So we have clock, we have reset, and we have count. And we'll make count configurable. So we'll say my $bitwidth equals parameter. So let's see. Less RTL integrator. Just gonna peek at. Oh, it doesn't look like he keep parameters in this one. Less RTL sequential multiplier has a bunch at the top. In fact, that's the exact one that I want. So there we go. So now we have a parameter for bitwidth. And then we need to instantiate some D flip-flops. So to do that, so we need a D flip-flop to hold count. So that implies that we have a count next. And then my dollar count D is equal to generate DFF D count. Width is equal to $BW, and then we'll leave everything else off. So then we instantiate it, $count D, instantiate, and then .dn is going to be count next. We get clock, we get reset. And then I think it's Q, and then count. Great, so now we have a D flip-flop that holds the state for count. Good, and so we'll start with a free running counter. So we'll say that, count next is equal to count plus $BW tick D1. So count next is always equal to count. Then we almost forgot our end module there. Yes, we'd be crying. And what do we need to add to top? So we probably want to know what the bit width is. So my $BW equals $DUT get param. So this would be less varef / top under sequential mult. So we're asking we're doing this. We're asking what the bit width is using the get param. So we're using the generated module to ask what the bit width is, because the generated module should know, or it might be set on the command line. So we aren't going to know as we're not going to know until generation time what the actual bit width is. And then now we can add our missing $BW. We'll add the -1:0 count. So we need extra space there. Good. So now we have the count, and then we probably want to add a little helper function. So always at pause edge clock. We will wait 1 tick, so we'll get the values after the rising edge, and then let's $display %t. So let's try to make this kind of reasonable. So we'll call that 6, and then we'll just print the number %d. So we're going to do $time divided by 100, and maybe we should kind of reduce what's going on up here. There we go. So it won't run forever. Throw a bunch of stuff on the screen, and then we got the count. Okay, good. So the monitor for standard out. Great. So that's where we're going. So this was counter. So we're gonna make gen module under name equals we said counter under gen. So of course can't modify a constant item in scalar assignment at line 19 in counter gen. So yep. So the way this works is that this is a hash. So this needs to be equals greater than, not equals. That was our first mistake. Undefined subroutine at line 19. So it didn't know about generator, it was looking for generate. Bum, bum, bum. All right, so that worked. So, no, not too many warnings. So this is our compiler is running. So we produced the binary. So we're just gonna peek at the comp.log to make sure there's nothing upsetting in here. So that's good. And then, so now we can run. Good. And it looks like we have a 16-bit counter, and it looks to be just counting up every cycle. So we have time in that. So it looks like it should go to 255. So let's make sure our test bench actually does that. So you can see that it rolls over at some point. Bum, bum, bum. Oh, this is 16 bits, so this will go on forever. So I should have been keeping better track. So let's go back to our counter gen, and we're going to make the default 8. So that's actually 255, not 255 times 255. So now we have an 8-bit counter, and everything should just work. Yep, there we go. So if we look at simlog.text, must have picked a weird one. So we can see it incrementing slowly, up by 1 every cycle. Then when we get to 255, it overflows and goes back to 0. Okay, great. So we have a free running counter. All right, so the next thing you might want is a counter where you can control the increment. So if increment is 1, we're going to be count plus 1. Otherwise, we're just going to be count. So this is a 2-to-1 mux. And this is a lot like looking at, our compact state transition table and saying, well, there's really only 2 things that can happen, is we could increment or we don't increment. All right, so we added a new input, so we should go back to our unit test, and we should add logic increment. For now, we're just going to assume that, let's go make this a parameter. So my $inc equals parameter name increment val is equal to 1. So the default is add increment feature. So we're going to say that the default is that it increments on its own. Okay, so that's cool. So then we need to do a little bit of work here. So if $increment, so now this port appears and disappears depending on whether or not increment is true. And so now we have if $increment this is what happens else. And what we used to have was the free running counter. So we'll assign count next equals count plus BW by 1. So now we have a parameter that we can turn the increment on and off. So I'm just going to move this comment so I can keep these nice and compact for a little bit. So my $inc. Okay, great. So increment, add increment feature. We'll say instead of add, enable increment feature. So we should probably ask about that. My $inc equals $dot get param inc. So now we know whether or not we have an increment. If $inc. So there we go, and then we need a driver for inc. So we're going to be a little lazy. We'll do random driver for increment, but we don't really care about having a driver for increment unless we are actually doing increment. And then the convention we're using in the class is that all inputs are driven on the negative edge of the clock, and so we'll say that inc is equal to $random. Cool. And then we don't need to muck with our dot interface because it's dot star. So by just removing the signal, we should be fine. So clean, run. So now we should get something that is randomly counting up, but we probably have errors. So we didn't spell parameter correctly. Parameter, good. And then let's be a little bit anal retentive. There we go. Inc does not exist in this instance. That's right, because we didn't call it inc, we called it increment. So it was saying that there's no parameter inc, that I'm actually looking for the parameter increment. And it might be helpful to go to our little display driver. And if $inc So now our display will have increment in it if increment is enabled. Otherwise it won't. So, so the prior cycle it's 179, the input was 1, so next cycle it's 180. There's increment, so 181. No increment, so it stays at 181. No increment, so it stays at 181. So part of the way to read these is that even though this is after the pause edge of the clock, this is last cycle's input and this is the current cycle's value. So last cycle's value of 1 causes 180 to become 181. Last cycle's value of 0 causes 179 to stay at 179. All right, so that, that seems pretty reasonable. We didn't overflow though, probably because we didn't run long enough. So let's say that this should be something like 1,000. 3. Yeah, we're pretty sure it overflows, but just in case. And maybe we should set the bit width a little bit smaller so that we don't have to. Maybe that was the right thing to do instead of setting it for a longer runtime. But it looks like it overflowed. So we're interested in the exact moment that it overflowed. So we didn't want to see anything weird happen. Great. So we have 0 to 255, 120. Great. So 255 plus 1 becomes 0. And it looks like it's counting just randomly. Good. So now we can we're fairly certain that the increment works. Okay, so the next thing you might want is if I'm building a stack pointer for a LIFO, so last in, first out, or a stack data structure, I need one pointer, and then the pointer increments on a push but decrements on a pop. Or if I have some sort of population counter for in-flight tasks, I'd want to have a deck interface. So we're going to go back to the module. $1 deck. Parameter name. Decrement. We're going to say that this is now a default. Doc enable decrement feature. And then we're going to say something like $inc equals 1 and so $inc equals 0 and $dec equals 1 and die can't have dec without inc. So I don't want to go write the cases where I only have dec, so I'm just going to say that that's not allowed. And then if I were doing a better job, you know, I'd actually enumerate the possibilities here, but these can either be 0 or 1. So we're going to do a 4-bit guy now. And then what we'll do is, what is it? Perl. Bum, bum, bum. Yep, that's what it is. ELSIF. Great. So ELSIF. So now what we're going to say, if increment and decrement so that's our new case here. So now we're going to need to do a little bit more work than we could probably do inside a normal assign statement. So we actually want something that looks like a mux, and we're going to switch on the values of increment and decrement. And then we'll start by defining a good default. So this is just, you know, there are 4 possibilities, but in most of those, count next is just equal to count. So now we only need to worry about the cases where the count changes, and that is only on, so we're going to ignore the 0, 0 and the 1, 1 case. We're just going to look at the 0, 1 and the 1, 0 case. Great. So then count next equals, so if we increment, so that is our count plus something over here. Let's add a little semicolon. And then we will similarly do this. Great. Cool, cool, cool. So now we can increment and decrement. So I think one thing I will say is we're kind of incrementing along here is that one of the things that I'm not doing that I would do if I were putting this into a library is that we've only been peeking at the output. I really should write some set of assertions to go with that. So if you want an example of me doing that, the bounding box iterator videos, we build a 2 or 3 dimensional counter for kicks because we needed a 2-dimensional counter, and that one does have a bunch of tests because I didn't trust my ability to write a 2-dimensional counter. And then I started adding features to it, and I didn't trust my ability to add those features, and so that one has much more thorough testing. But for this is sort of what bring up would look like, and then probably what I do is come back and then write in as many assertions as I could. All right, so now we have this. So we have inc and dec. So we're just gonna copy paste that code. So if dec. And this is kind of some laziness too. You know, if I were doing a better job, you know, I would actually start doing the cross products of these things. But right now, since we're kind of working in a narrative arc and we want to close out as quickly as possible, we don't want to do that. So now we have dec. So now we need to go back, and we'll just try and work our way top to bottom. But we've already done increment. So decrement should just be a matter of copying and pasting. Decrement. Perfect. Done. So then we need one of these. $dec. Awesome. Dec. Awesome. So now we have the itty bitty counter, so we're not going to be in trouble. So now we're gonna need to do some work here. Notice that we don't have a default case, because in the default case we don't have a default case for our if-else tree here, because in the default case there doesn't need to be stimulus. And then we will do this. Don't worry, it's still pretty random. And then we need one of these. So we're going to need to close this guy. Increment and decrement. Great. So this will probably fall apart on us, but we're getting there. Great. So it looks like it is, we're incrementing and it's going to 0. So less simv simlog.text. But it looks like decrement isn't working. And that is because we have a copy paste error. So the danger of copy pasting code is that if you copy it but forget to change it, your code's wrong. So great. So we in reset for a little bit. So this is, I think, the end of reset. And then we have a decrement, so 0 becomes a 15. And then we have 15 and 1 becomes a 0. So 12 plus 1 is 13. 13 and nothing happens is 13. 13 plus 1 is 14. Plus 1 is 15. So good. So I think we can sort of call that a victory on the increment and decrement there. All right. So the next thing you might say is, if I'm building a custom stack or a custom sequencer, there might be a finite number of sequences that I'm interested in, right? So if I'm thinking about building, a sequence machine that has 13 entries in its table, then I only need to count to 13. Or if I have a stack with only 3 elements in it, then I only need a counter that counts to 3. So I don't want to get in the habit of, needing to add extra logic outside of the counter to do this. Instead, what I'd like to do is have a min or a max. And so what we'll call it is, we'll call this upper bound parameter name upper bound. And by default, we will set it to -1. Upper bound exclusive. Great. And then then what we need to do is we're going to set a default bit width. So what we're going to do, and then we're going to create clog2. It's going to be return seal log2 of $under 0. There's clog2 of $UB. So now we have an upper bound. $def BW. So now we have a default bit width. And then, so actually we'll call this the minimum bit width for now. And then what we'll do is we'll go, okay, the default bit width is equal to $UB greater than 0. Then it is. So if that is true, then we'll use this min BW number. Otherwise, we're going to use 8. We've been doing 4. Okay. Great. So now we have that going. So now what will happen is that the upper bound will determine the default bit width if nobody's interested. And then what we'll do is we need to check that $bit width is greater than or equal to $min bit width, or die not enough bits for upper bound. Great. Great. So I don't think anything we've done so far has actually changed the functionality, so it should just still work. Unless we probably have a Genesis 2 error. Yeah, we do. Illegal declaration of subroutine counter. Why does it not like this? It looks like we're lazy here. Left that. So that wasn't fixing our problem. That was just fixing a flow issue. So why does it not like this? Semicolon. Semicolon's my guess. Clog2. And then functions get wrapped in squiggly brackets. We just did this like 20 seconds ago. Not enough bits for upper bound at interesting. But we only want to run this test if that's true. So what we actually want to check is, $UB greater than 0. So if it is greater than 0, then we need to do this. Okay, good. Good. Did I write $and? No, I stole the $, from bit width. There we go. Not enough bits for upper bound at line 13. So UB is -1. So this should be false. So let's help ourselves out here with, let's just print out $UB, $min BW, and $BW. All right. So that's not the best help message in the world for an error. So -1, nan, and 4. So -1. So this should have been false. This should have returned that is odd. So I might be blowing a gasket here. So UB is -1. UB is -1. -1 is not greater than 0, so this would have been false. So it should have automatically skipped all of this. Maybe there's some order of operations thing that I am forgetting. So we'll do that just to make life a little bit easier. I think maybe this would be the one language where ors become before ands. I don't think so. I guess so. All right, so let's take a quick peek at counter under gen. So upper bound was -1, bit width was 4, increment was 1, decrement was 1. We get the counter we expect. Good, 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 good. Cool. So now we have a way to enable the upper bound. So unfortunately, that means that and $UB equals -1. And then, this is getting sort of fun. And UB equals -1. And then this should actually be else if $increment equals 0 and $decrement equals 0 and $UB equals -1. Not supported. Great. So let's quick check to make sure that we're not accidentally hitting that. Great. So it looks like it still works. Great. So now we have the case where we have upper bound. So this can stay the same, but what we're going to do now is we're going to add a new signal called up. And we're going to go logic up. And we're going to assign up equal to count equal bit width tick D. And number is UB, but what we're interested in is UB minus 1. So if it's 4, it should be 3. Tick $UB minus 1. Great. So now we have 2 new cases. So we have the case where it's at that bound or it's not, that it's at that bound or it is not. So we don't need to worry about the other cases, but in the case where we are decrementing, we also need a down. Okay. Case X. So in the decrement cases, we don't care if we're at up. In the increment cases, we don't care if we're at down. This is 1, 0. There we go. So we need a little bit of logic to tell us if we are at the upper part or we're at the bottom part. So in this case, where we decrement at UB, when we decrement at 0, then we should become UB minus 1. And then if we increment on up, then we should become 0. We'll make a note here for later that a good generator would detect $UB as power of 2 and skip all of this nonsense. Skip all of this. Great. Up, down, great. And the reason that we wrote it this way is that we wanted to detect if somebody was setting an upper bound, because otherwise folks might know that they can just set the bit width. Similarly, somebody may want to set an upper bound for a specific bit width, so they want to register holding zeros in some of the leading bits for some reason. Theoretically, somebody shouldn't be defining bit width if they're designing the upper bound. Unfortunately, I don't want to go the other way. So that's why we're kind of doing it like this. All right. So if increment and decrement and upper bound are greater than 0. Great. And then I don't, because we're not actually doing any tests, don't actually need to check that, we're doing what we expect. Just for some consistency's sake, we'll grab the upper bound. Let's make sure I got the name right, upper bound, and then we called it UB. Hey, we could write an assertion. Simple test. So if $UB is greater than 0, assert that count is always going to be less than tick D tick UB. So that should be true in general. You know, assert. Great. So I think that's it. So we're going to need a way to set the parameter on the command line. So I need to peek at what it is. I think it's Genesis under params. Might be what I did. Wow, it's kind of buried in here. Boo. And then we're looking for, yep, Genesis under params. So Genesis under params equals and then let's see. So I think it was top under counter under gen dot my under counter under gen. So was it my under counter gen? Yep. And then we called it upper bound, and we'll set it to 5. And it should yell at us if we mucked that up. Oh no, so we did mess it up. But we messed up this part because we forgot to put our case statement inside an always com block. Module. So usually this means that we didn't close something that we were supposed to, as we have forgotten to close this begin end. Good. So that error was token is end module. This usually means that we forgot to close one of our scopes. So it saw this begin and then hit an end module where it was expecting an end. And I don't think it even told us. Yeah, it went to the end of the file and then sort of said, nope. So the parser there can be a little bit unforgiving. It doesn't like my assertion. So the issue is it doesn't like anonymous assertions. So we should give this a name, boundiness. So now we got rid of that lint error. All right. So sim log text. So let's see what we got here. So we're at 0. We decrement by 1. We get a 4, which makes sense because 5 minus 1 is 4. Decrement. So we are looking for a at 4, but we get an increment. We go to 0. Good. And then otherwise, it looks like we stay the same on 1s and 1s. A 2 in an increment is a 3. So good. A 0 in a decrement is 4, but we had that. So we want 4 in a decrement is 3. 3 in a decrement is 2. Good. 2 and nothing happening is 2. And then 3 and nothing happening is 3. Good. All right, so now we have a custom maximum. Cool. So we could play a similar game with the minimum. And here, this is the wrong file, counter gen. So we could say my dollar lower bound equals parameter name lower bound. So we'll call this 0, and we'll say lower bound inclusive. Good. And then we'll help ourselves out. $LB must be greater than -1. Die. Counter isn't signed. And so then we would just go and peek into this code and $LB -1 and then this 0 becomes a $LB. Good. And $LB equals 0. And $LB equals 0. And $LB equals 0. So you might as well. So the way we've written this, you have to have an upper bound if you're going to change the lower bound. And you know, certainly one thing to do would be to go in here and look at the cross product. And a few of these overlap. You know, so we could even play some games to kind of get that organized. So let's see. We're going to do the same thing. So top under counter under gen dot my under counter under gen dot lower bound equals, and we'll say 1. Then we forgot to close our backticks. This is one of the more common mistakes, so I think there's a check, making sure that we do that before the end of the line. All right, great. So now we can look at our symlog. So we have an interesting problem that when we're coming out of reset, we start in 0, which could be certainly a problem. So one way to fix that is to change this to a counter, to a less than equals. But it'll still come up as 0 and reset. Yep, and so that's how we overflowed, because we did a decrement on a 0, and then it sort of pushed us into a bad realm. So, you know, we could certainly make this a little more robust by making this an actual comparison. We're still going to have the problem that if we're at 0, it's not necessarily going to behave the way we expect, but we should recover a little faster. Yeah, so we're at 0, which is below the lower bound, so decrement puts us at the upper bound. So good. So we got rid of all the illegal behaviors. The design got a little bit more expensive because a comparison, like an equals equals, is just a a bunch of AND gates and a big OR gate. So it's not that bad. It can still be fairly expensive. A comparison is almost like a subtraction. Is you're inverting one of the sides, adding them together, and then looking for a sign bit that's coming out. And then depending on the sign value, you know whether or not it was less than, equal to, or so on and so on. Cool. So that was custom minimum. And then it looks like we have been at this for a little over an hour. So I think we will call that for today. But this is sort of how you would take one module that sort of has a similar purpose and sort of pack a lot of features into it. And if we were really clever, what we'd start figuring out how to do is how to start combining these sub things together so that we don't need to have a huge enumeration, right? Is we certainly wouldn't want to get into the habit of going, okay, increment and decrement gets us 4 base configurations, and then now we have upper bound, which gets us to another 8 configurations. We wouldn't want to have a full 8 set of configurations just to accommodate that set intersection. So what we might want to do is maybe there's a trick that would let us write the statement in a way that avoids the problem, or writes this, or 8 isn't too bad, so maybe it is worth sort of working through. And certainly this is not a bad way to go with the die statements, letting people know that, hey, this isn't a great idea, so please don't do that. And certainly that is okay. Well, I hope everybody has a wonderful Tuesday evening. I will see you all next time on Hardware Design, and let me know if there's anything else that you guys would like me to take a look at in maybe a future evening session